We designed our vehicle using wood, PVC piping, lawnmower wheels, and elastic tubing. It was almost 19 inches wide and roughly half a meter long. The vehicle you see in the pictures was our fourth model. Initially, we tried to design our vehicle with a falling weight system, but it required a lot of weight to get it to move and was very inconsistent. We moved things around and tried getting bigger wheels, but nothing solved our problems consistently.
Next, we tried to combine a falling weight system and a wind-up rubber band system. Once again, the falling weight system was a major issue. So, after some time, we decided to ditch the falling weight system altogether and use a wind-up rubber band system. We found bicycle wheels to use as bigger wheels, but we had trouble figuring out how to attach them to the axle. As a result, we ended up sticking with our lawnmower wheels. We also got a different piece of wood for the base of the car because our initial wood base was extremely heavy and created too much friction between both the wheels and the ground, and the axle and the piece keeping the axle in place.
As you can see from the photos, the elastic tubing wound up on the back axle, causing it to turn when we released the car. We put our elastic tubing system on the underside of the car so that when the tubing had unwinded all the way, it would simply fall to the ground instead of start winding up the wrong way and making the car go backwards. The elastic tubing was so effective in getting our car to move for a number of reasons. The elastic tubing had a lot of elastic potential energy, which was converted into kinetic energy as the elastic tubing unwinded off the axle, therefore allowing our car to move.
Our vehicle's motion was linear, but we used rotational motion to power the linear movement. Rotational motion involves an object rotating about an axis. The four wheels on our car all rotated around the axes, thus using rotational motion. Linear motion involves an object moving from one point to another in a straight line. Our car had a linear motion as it moved from the starting point to the pins.
It took us a very long time to successfully get our vehicle to move. Initially, we used a guess and check system while we tried to build our vehicle, but when we applied physics, that was when we had the greatest success. We had to apply force to the axle in order to get it to rotate. This rotational force is also known as torque. Torque is the quantity that can change the rotational motion of an object. We used a larger axle than we initially started with because the larger the axle is, the less force is needed to rotate it. We applied torque to the axle using our elastic tubing system. To make sure that the wheels rotate along the axle, we had to ensure that there was some friction between the wheels and the ground so that the wheels wouldn't spin out. Acceleration also played a role in getting our vehicle to move. When first built our vehicle with the falling weight system, our acceleration was so little that it barely moved besides the initial movement. We had so much success with the elastic tubing system because the car accelerated quickly and maintained a higher velocity for a longer period of time. We also considered momentum when building our project. Momentum is the mass of an object multiplied by the object's velocity. When we build our car, we try to create a large momentum by raising the car's velocity. We were hesitant to raise the mass too much because in our initial trials, when the base was too heavy, it pressed on the axles and made it difficult for the car to move. Possibly, had we situated our axles differently, we could have made the car heavier, thus making the momentum higher.
Overall, our vehicle was average. Out of 4 trials, the vehicle knocked down 18 pins total. On one of the trials, our vehicle did not hit any pins at all because it veered extremely far to the left side. This was caused by the axles of our car because they were not completely straight. To ensure that the car did not veer to one side, we should have made sure the axles were in place and couldn't move too much, and we should have made sure that the U-shaped pieces holding the axle in place were perfectly straight across from each other. We also could have improved our car by making it go faster and further. This could have been accomplished in a number of ways. First, we could have used bigger wheels. This would increase the distance per one rotation of the axle, thus making the vehicle travel a larger total distance. We also could have wound up the elastic tubing more tightly. This would have caused more rotations of the axle, and the rotation would have occurred faster because the force pulling on the axle as a result of the wound up tubing would be greater, thus causing an increase in both speed and distance. We also could have applied the same elastic tubing system we applied to the back axle to the front axle. Having both axles spinning would increase both speed and distance as well. We also could have improved our vehicle by making it more effective when it came in contact with the pins. Our vehicle was small, so it was less successful in knocking down pins than larger vehicles. However, we made the conscious decision to compromise pins for speed and distance because we were worried about how far our vehicle would go. That being said, we could have added a plow of some sort to the front of our car to help knock down the pins.